So this talk is going to be picking up on a lot of the themes that Hayata talked about in his nice very first opening talk. And so I should mention the joint work with Oscar Lauch, who was my undergrad summer student, but is now doing a master's in Waterloo. Okay, so the theme of this work is, well, it's a very mathematical work, pure mathematics, and it's meant, it's a mathematical program, really. It's a multi-paper, multi-year program aimed at answering this question: which gates can be easily performed fault-tolerantly? Okay, so we know that, we can do we have fault-tolerant universality. We can approximate any gate fault-tolerantly, but how do we achieve that? So what are the basic building blocks for quantum universality? Okay, so some gates we can do approximately, but some gates we can do directly, some gates we can do perfectly. Okay, so the elementary building blocks of quantum fault tolerance, this is the box question, is really just a high level, base English language way of saying, the specific mathematical question we're going to be answering is, what are the gates of the Clifford hierarchy? Okay, so Hayata mentioned it, but if you don't know what the Clifford hierarchy is, I'm going to go into a lot more detail about it and why it's important. It was first invented by Gottesman Chuang in '99. So at that point, stabilizer codes had been invented, error correction had been invented, but people were still working out the details of fault tolerance. So the now standard technique of using gate teleportation and magic states, Shor constructed the first example, but to turn it into a real scheme, that was this paper here. And since then, so that was 26 years ago now, a lot of people were studying what are the gates of the Clifford hierarchy. So Gottesman Chuang gave a definition, but only gave examples of various gates in the Clifford hierarchy without saying an explicit list of what they are. And people have been studying that ever since, including Gottesman Chuang, Shor, their co-authors, lots of people. So it's been a well-studied question for 26 years. Okay, the second very important question, so as Hayata mentioned, fault tolerance introduces a huge amount of overhead into quantum computing. And so we want to reduce that as much as possible. So that motivates the second question: which of these gates can be efficiently performed fault tolerantly? So performing fault tolerant gates using this technique consumes a resource called magic states, and they're very expensive. You need loads of them. So any way that we can cut down on how many resources we need, that just means quantum computing, fault tolerant quantum computing is going to happen faster if we can get that hardware resource cost down. Okay. So mathematically, what that question translates into this program is, which hierarchy gates have this property that are called semi-Clifford? So I'll explain what that is. That was defined by Zhen Chen Chuang in 2008. Okay, so they're basically some gates that you can perform fault tolerantly. Some of them, a subset of them, you can perform with magic states half the size, and that's what's called semi-Clifford. Okay, so as I mentioned, both of these questions have been studied for a long time by lots of authors and giving examples or partial results. But in this work, we're going to give a complete answer. So we're going to completely answer the question of what are the gates of Clifford hierarchy. We gave a complete list. We also prove that for one qubit or qudit, for qudit of any odd prime dimension, they're all semi-Clifford. Okay, so that settles the question, these two questions, in the limited but practically very relevant case of a single qubit or qudit gate. Okay, so to give you an overview of this talk, first I'm going to review gate teleportation and the definition of the Clifford hierarchy. Then I'm going to go into some of the mathematical tools we use to prove this result, such as the discrete Stone-Von Neumann theorem, something called conjugate pairs, which is a new concept to this work, and the Pauli basis and how it relates to proving this theorem. Okay, and then we'll give the main result, which is basically an explicit description of an exhaustive list of all the one qubit or one qudit gates. And because we've listed them all, that's also allowed us to give us for the first time a number of how many gates are in each level of the Clifford hierarchy for every dimension. And then the proof that all of them can be performed efficiently according to this definition of semi-Clifford. And hopefully this time I'll talk a little bit of sketch out the proof, although it's a bit technical mathematically, so I'll just give a very high level overview. Okay, so quantum gate teleportation. So as I mentioned, quantum gate teleportation was introduced to promote the gates that you can easily do fault tolerantly in stabilizer codes. So which gates can be easily performed fault tolerantly? So for example, transversely, okay, not necessarily transversely, but usually transversely. So typically we take the Clifford gates as a group of gates that we can do easily fault tolerantly. So without needing some special scheme like gate teleportation. Okay, so So the definition of the Clifford gates, as you probably know, is it conjugates the Paulis back to Paulis. Okay, so the set of Paulis, or the group of Paulis, I've labeled by C1 suggestively, and the group of Clifford gates is C2. Okay, and the Clifford gates form a maximal non-dense subgroup of the unitaries. Okay, so what that means is that you cannot approximate any gate using Clifford gates, but it's the largest subgroup of the unitaries that has this property. So as soon as you are able to do one more gate beyond the Clifford gate, you can now approximate every gate that way. So in order to do fault-tolerant quantum computing, universal quantum computing, we know that we can do the Clifford gates easily using usually typically transversal or similar technique, but we need to be able to perform at least one other non-Clifford gate to achieve universal fault-tolerant quantum computing. Okay, so the typical way that we do this, introduced by Gautam Chuang, is to use gate teleportation. So I'll introduce that protocol step by step. So here is the normal teleportation protocol. Okay, so it's broken up into boxes. So you prepare the Bell state, then Alice performs a Bell measurement on her pair, communicates the result, and then Bob performs a correction operator on his line, and at the end of it, he has the initial input state that Alice tried to send him. Okay, so now we'll modify this slightly. So all of I've done here is I've introduced a G and a G star at the bottom of Bob's line. Okay, so that actually does nothing because of the identity. And then introduced a G at the end of Bob's line, and what that does is changes the state that Bob gets from psi to G of psi. Okay, so we've modified this protocol. So at the end, Bob receives not Alice's state, but Alice's state with a gate applied G to it. Okay, and the way that this protocol has been modified, the G and G star do nothing, and there's a G at the end. Okay, but we've grouped the G and G star so that G is in the state preparation stage. So instead of preparing a Bell state, you prepare a Bell state and apply G to one half of it. And then instead of the normal correction operator, which would typically be a Pauli, you instead do a Pauli conjugated by G. Okay, so that motivates the definition of the third level. The third level are all the gates that when you conjugate a Pauli, you get back a Clifford gate. Okay, and why is that important? Because these correction operators are Paulis conjugated by G. So whenever G is third level, that correction operator is Clifford, which means that you can do it fault tolerantly, which means this whole protocol is now fault tolerant, except for possibly the preparation stage where you prepare G applied to the Bell state. But there is a protocol for preparing that fault tolerantly. Okay, and it's better to apply G if G is like not easy to apply to an expendable Bell state, where if you screw up, you can just throw it away and try again, rather than to your sensitive data. Okay, so third level is really important because you can prepare this magic state. You can have as many attempts as you want. You can store the magic states until you need them, and then you use them as a resource to apply G, and you can do it in a fault-tolerant way. And G, when G is outside the Clifford group, then this protocol allows you to achieve quantum universality. Okay. So the Clifford hierarchy is now defined inductively as the gates G that when you conjugate the Paulis, you get something one level down. Okay, so we've seen that this protocol allows you to fault tolerantly do third level gates. So we can now add that to the set of gates that we can do fault tolerantly, which means that if our correction operator is third level, we have a protocol for doing that. So that's what we define the fourth level gates to be, the things where the correction operator is third level, and you can keep doing that. So it gives you a nested sequence of sets, all of which you can perform fault tolerantly as long as you can do the lower level fault tolerantly. And when you get to the bottom, you could just use the basic third level protocol. Okay, so C1, C2, C3, that labels the levels. C1 is a Pauli group, C2 is a Clifford group, C3 is probably the one you're most familiar with, like the T gate is C3, and it just goes on like that, keep getting bigger. Okay, and C1 and C2 are groups, but they're no longer groups after that, which makes it really hard to study mathematically. Okay, so one thing about this protocol you'll notice is that it's based on the the old teleportation protocol, where you had a separation of parties between Alice and Bob. But inside a chip on a quantum computer, you don't necessarily have a separation of spatial separation. So that is unnecessary. So that motivated this definition of semi-Clifford gates, which allows you to do a more compact protocol because you use a better a protocol for teleportation that's more suited towards this task, as long as the gate has a special form. So if the gate that you're trying to perform looks like a Clifford times a diagonal gate times another Clifford, then there is a more compact protocol here. So you can check that this works. But the main difference is that the magic state, you just apply the diagonal part to a single qubit or qudit, okay? So notice in the previous one, we had a Bell state, which is 2 qubits or qudits, right? So the magic state in the standard protocol is twice the size of the gate that you're trying to do. Whereas if it's semi-Clifford, if it's semi-Clifford, it's the same size, okay? So that's where the semi comes in. The magic states are half the size, okay? So for n qubits or n qudits, the magic state is n qubits, okay? So you're probably only familiar with the typically you'd be familiar with the T-gate protocol, so that is actually coming from this semi-Clifford one. You probably have not seen this outdated one, right? So that's why the T-gate is really big, because it's the simplest semi-Clifford one. Okay, so just to recap, the Pauli group C1 are the gates built from Z and X. The Clifford group are those that can be easily performed fault tolerantly, but that's not enough. Higher level gates can be performed fault tolerantly as long as you have access to suitable magic states. And semi-Clifford gates are those that can be performed efficiently with magic states, in the sense that their magic states are half the size. Okay, and so to recap the two questions we're going to be answering, what are the gates of the Clifford hierarchy? So I gave you the definition, but that doesn't tell you what they are, right? It only tells you what properties they satisfy. So we have to give the list of all of them that they are. And which of these gates are semi-Clifford, okay? So this result, so the theorem I'm going to tell you about is about 1 qubit or qudit, okay? So there are some known results only in the qubit case that I'll talk about. So for 1 or 2 qubit gates, all gates of the Clifford hierarchy are semi-Clifford, so that's due to Zhen Chen Chuang. And also, I should mention that the proof was like by computer, basically, so it doesn't give much insight into why it works. It's kind of an exhaustive computer proof. And for more than 2 qubits, it's no longer true that all gates are semi-Clifford. So that's due to Beige-Shore, Algorithm, and Mo-Chan. So what this graph shows is when there's a black dot, that means there's a theorem that says all n qubit gates at the kth level are semi-Clifford. When there's a white circle, it means there's a counterexample, and when it's red, it means it's open. Okay. And in the qudit case, there were no results really about being semi-Clifford, but there were some results about what are the gates of the Clifford hierarchy. So Kui, Gautam, and Krishna classified the gates that are in the Clifford hierarchy that are also diagonal. Okay, so it's a restricted set, but has a very nice classification. So it basically, the diagonal entries look like you're taking a primitive root of unity and raising it to a power, and the function that you raise to a power of is a polynomial. And so it gives a very nice description of what these diagonal hierarchy gates are. And the level of the Clifford hierarchy that such a diagonal gate is in is determined by m, which is the root of unity that you're raising to the power, and the degree of the polynomial. Okay, so very nice classification of the diagonal gates. But of course, there are non-diagonal gates, and that's what, in this work, we're going to extend this classification to the general non-diagonal case. Okay, so all right, so now I'm going to talk about our work. Okay, so first I'll talk about the mathematical tools that we use. So the discrete Stone von Neumann theorem. So this was a foundational result of early quantum mechanics, where at that point there were different versions. So there was a matrix mechanics and there was wave mechanics, and people didn't understand why there are two theories of quantum mechanics and why they give the same answer. And von Neumann gave the answer, which is that they are unitarily equivalent. So they're actually the same theory, even though they look quite different. And in the finite dimensional case, this has a very nice, simple picture. So if we have two gates and they satisfy the canonical commutation relations, which means they're both of order d, right? So these are qudits of dimension d. They're both order d, and when you commute the gates, all that does is introduce a primitive d root of unity phase difference. Then we say they satisfy the canonical commutation relations, okay? And so you'll notice that z and x satisfy the canonical commutation relations, right? That's the prototypical example. But if you conjugate z and x by some gate g, then that's also going to satisfy the canonical commutation relations, because g preserves those relations. And what this theorem is saying is that if you have gates and they preserve the commutation relations, they must have come by conjugating z and x by g. So this actually gives a bijection between unitaries g mod phase and these pairs of gates that have the right commutation relations. Okay, so this actually allows us to study hierarchy gates by studying their conjugate tuple, which at first seems counterintuitive because you were studying gates G by instead studying a pair of gates, which seems like more information. but actually it's a really nice construction that allows you to study the Clifford hierarchy in an inductive way because of this theorem, which tells you that a gate is of level k plus 1 if and only if the gates that you get by conjugating z and x by g generate kth level gates. Okay, so it allows you to reduce the study of the k plus 1 level to if you are to the understanding of the lower levels. Okay, let's skip the multi-qubit case. Oh, I think the clicker's broken. Okay, so let's take a semi-Clifford gate and ask what does its conjugate pair look like. So basically, we're going to take z and x, and we're going to conjugate it by this gate C1 DC2, which is the general form of a semi-Clifford gate, and ask what does it look like? What does its conjugate pair look like? So what does it look like when you conjugate z and x by this gate? Well, let's do it one gate at a time. We're starting with C2. So if you conjugate z and x by C2, you get some Pauli. Then if you conjugate those two gates by d, you can commute the d through the z, and you can commute the d through the x, and that changes one of the d's. But what you end up getting is some diagonal gate times the power of x. Okay. Now, if we conjugate all of that by C1, we have this nice simple form where you have a diagonal in both u and v. You have a diagonal gate multiplied by power of x, a diagonal gate multiplied by another power of x, and all of them have been conjugated by some common Clifford C1. Okay. So what about the converse? If we have u and v and it looks like this, right? We know that u and v is in bijection with some gate. So is the gate that it's in bijection with, is that semi-Clifford? And the answer is yes, okay? And that's like a key lemma in this work. And this part is actually quite complicated, the converse direction. And that's kind of one of the key technical insights. Okay, and we can try to simplify this condition a little bit. So what we can use is the fact that the group of diagonal gates does form a group, even though the kth level doesn't. And the almost diagonal gates form a group. So we call a hierarchy gate simplified if its conjugate pair is made up of almost diagonal gates, so a diagonal times the power of x. And okay. We call it simplifiable if it's a gate is simplifiable if it's Clifford conjugate to a simplified gate. And this gives us another important equivalent notion of being semi-Clifford. It's semi-Clifford if and only if it's simplifiable. So this tells us what it looks like in terms of the conjugate pair description, what it means to be semi-Clifford. So this is also an important technical tool. Another key tool is to use a Pauli basis. So as you know, the Pauli gates form a basis for the set of matrices, d by d matrices. And the Pauli support of a matrix are those Paulis with non-zero coefficients in the Pauli basis decomposition. So for example, we can visualize the Pauli support of a d by d matrix using like a grid. So here's a random matrix, z squared plus x, whatever. So anyways, that's the Pauli support. Okay, we only care about where it's non-zero in the Pauli basis. Okay, and it turns out that semi-Clifford gates have a very nice description in the Pauli basis. So it's a geometric description, which is that a gate is semi-Clifford, or simplifiable rather, if and only if the Pauli supports of the two gates u and v that correspond to g are contained in parallel lines. Okay, so that gives us a nice geometric way of understanding what a semi-Clifford gate is. Okay, so I'll just sketch the proof of how we prove that all hierarchy gates of any level k for any qubit dimension d, they're all semi-Clifford. So we do it by induction, and the base case of Pauli is easy because they're obviously all semi-Clifford. So we look at a k plus 1 level gates, and we assume that u and v, which are one level down, are all semi-Clifford. Okay, so we can then prove that we know that they're Clifford conjugate to almost diagonal gates because we have this characterization. However, they might be Clifford conjugate to almost diagonal gates using different Cliffords. So we have to show that if it's true that they're both Clifford conjugate to almost diagonal gates, we can actually use the same Clifford. And that means that it's simplifiable. And then we just use the lemma that we talked about before to show that, to conclude that the gate G is semi-Clifford, okay? Because simplifiability and semi-Cliffordness are equivalent. Okay, so that establishes our main theorem, which is that for any odd prime dimension D, every one qubit hierarchy gate is semi-Clifford, okay? So they can all be performed efficiently using these smaller magic states. And it also gives us a nice form for every hierarchy gate, C1, D, C2, okay? But the problem with this form is that it's highly non-unique because you can write the same gate in this form in many, many different ways, okay? It's not a unique normal form. So that is the next step. How do we make this expression unique? So we give a precise way of writing every hierarchy gate. So step one is to give a normal form for the Clifford matrices, or so the Clifford gates. So let N be the group of Clifford permutation matrices. So those correspond to affine linear transformations. So these, if you take any product of a diagonal Clifford and a permutation Clifford, those products form, the set of all those products form a subgroup. So we just take a left coset representative for each of those cosets, and we can get a nice normal form for any Clifford. So any Clifford, one qubit Clifford gate or qubit Clifford gate can be written uniquely in the form MDP, where D is a diagonal Clifford, P is a permutation Clifford, and M belongs to this finite set of coset representatives, which is some diagonal Clifford times the Hadamard. Okay, so we have a nice way of writing every Clifford uniquely in this form. So we can then plug that in to the C1 DC2 form of any semi-Clifford gate, which is every hierarchy gate, rearrange things. So this gives us a nice way of writing every Clifford hierarchy gate, right? It's either Clifford, in which case we already just gave a normal form, or if it's higher level, then it looks like MDC, where M, again, is one of those finite coset representatives, one of the finitely many coset representatives. D is a diagonal Clifford, except we mod out by the diagonal Cliffords. Sorry, D is a Kate level gate, diagonal Kate level gate, which was classified by Puig, Krishna. So we know exactly what those are because they correspond to the polynomials and the phase polynomials, okay? And yeah, so this gives us an exact way of writing every hierarchy gate for one qubit or qudit as a product of three elementary gates, each of which have been precisely classified. So because we know all of those sets, we can count them. We can then count the number of hierarchy gates at every level for any prime dimension. So this gives us a count of the hierarchy size, the size of every hierarchy, Clifford hierarchy level. Okay, so yeah, that brings us to the end. So again, we've answered the question, which hierarchy gates are semi-Clifford? So for all odd primes D, and also for qubits, but that was known already, all single qubit hierarchy gates are semi-Clifford. And what are the gates of the Clifford hierarchy? Well, we showed that they can be expressed uniquely using our normal form. So they're all a product of three elementary gates, with each of which has a simple form, which allows us to count them. Okay. So in the future work, so as I mentioned, this is a long mathematical classification program. Because the Clifford hierarchy is such a fundamental algebraic structure in fault tolerance, I thought it was worth it to try and figure out what it was. And people have been trying to figure out for 25, 26 years. And so we want to continue this work and try to figure out what are all the gates in the Clifford hierarchy for more numbers of qubits or qudits. Yeah, so for example, for two qudits, it's unknown whether they're all semi-Clifford or not. So we're working on that. And it does actually get much, much more. So a lot of the techniques that I talked about here, they do generalize to multiple qudits. However, there are also very significant differences between the 1 and 2 qudit cases. So it actually does get much more mathematically complicated. But we're working on it. And I also want to mention that although the origin of the Clifford hierarchy was in fault tolerance, and that is also kind of the main reason why a lot of people are interested in it. That's kind of the reason why when I give this talk, I put that as the main motivation, but it's not the only motivation. So another reason why, the reason why I got interested in the Clifford hierarchy is because of the relationship with magic states. So magic states are resources that allow you to take a classically efficiently simulable scheme of stabilizer quantum mechanics and promote it to universality. So it's really fundamental to understanding where does the power of quantum computing come from, because you have this efficiently simulable theory, you throw in these magic states and they become universal. So that's, it's in the name, magic states, right? So there's something special about these states, and they're connected with the Clifford hierarchy, and the level of the Clifford hierarchy is connected with their usefulness as a resource, and is connected with all kinds of other complexity measures and learning and things like that. So I think that understanding the structure of the Clifford hierarchy, understanding the structure of magic states is also not only fundamental to fault tolerance, but also to understanding quantum advantage. I just want to point out a potential application of knowing what all the gates in the Clifford hierarchy are. So, everybody knows about the T gate, and everybody knows about decomposing gates over Clifford plus T. But there's not a specific reason why we only use Clifford plus T, other than simplicity, right? So, because it's easy to produce one T, many, many, many copies of T gate magic state, but one day in the future we might have very precise experimental control over these quantum systems, and it might become just as easy to produce anything in the Clifford hierarchy. And it may actually be more efficient to, rather than compile all of our gates over just a Clifford plus T gate set, to compile things over Clifford plus third level or Clifford plus hierarchy, right? So it may actually, by knowing what all these gates are, it may actually lead to much more efficient circuit compilation, for example. So there are lots of, because it's such a fundamental object, there are lots of potential applications, lots of potential insights to be gained. So yeah, so we're going to continue classifying this object. So thank you.
Thank you, Nadish. We'll take questions now. Does anybody have any question?
Yeah, thank you for the talk. I mean, the obvious first question probably is, what about prime power dimensions? Have you considered those, or is there any reason it's applicable?
So the reason why we haven't done it yet is because the prime case is easier for obvious number theoretic reasons, and yeah. So basically, I think the order in which one would, I think the optimal order is to work out the prime dimensions first. Because there's lots of parameters, right? There's NKD, the number of qubits or qudits, the hierarchy level, and the dimension of the qubit or qudit, right? So my thinking is that the easiest way will be to first fix the dimension to be prime, and then work it out, and then hopefully work out all n, all k, right? And because it gets much more complicated mathematically when you move to other prime power or composite dimensions, but that is on the agenda, right? So I have a new PhD student, and he's interested in potentially working on composite dimension. So it just adds another level, but the thing is, the ideas that you need to do the composite, most of the ideas that you need to do the composite or prime power case, you have to work out in the prime dimensional case first, right? And it's easier to do it in the prime dimensional case because there isn't the extra complicating factor of composite dimension. So I think it just makes more sense to first work out the prime dimension and then find what additional ideas you need to make the composite dimension case work. Make sense? Yeah.
Sure.
Nice talk. You gave this motivation earlier on your first slide of the reason we want to understand the levels of the Clifford hierarchies gives us some clue about which gates are easier to implement in a fault-tolerant protocol. So is the motivation story that the higher up you are in the Clifford hierarchy, the harder it is to implement the gate?
Yeah, it seems so. I mean, the third level is optimal, right? But then if you want to do a fourth level gate, you have to also do a third level correction, which means you also have to have a third level magic state. So doing a fourth level or fifth level gate requires you to also have resources for the lower levels. So that's why it seems like the best resources are third level, and they seem to get worse as you go up.
So what are your thoughts on the fact that this Clifford hierarchy is defined very exactly, right? Like it's an exact set of things that satisfy a certain algebraic condition, but in practice, maybe you're okay with your gates having a tiny bit of error, right?
Yeah.
Like, is there some approximate notion of this where you're like just you're epsilon close in some norm, or what is like the not algebraic version of this story where you don't mind a little bit of error?
I mean, I think they would be within. You'd have to have the exact case, I think, to know what the approximate case is, right? It would be basically approximately the exact case, right? Like the hierarchy gates would be approximately the whatever the. I think I don't know, but that's just my impression, my initial gut feeling.